We're going to take a quick look at the kinematic equations. On the equation sheet, they look like this, which can be intimidating at first glance. We're going to take them apart one by one. The first one you've already seen when you looked at the physics classroom. VF equals VI plus AT. The only thing is you looked at it in a slightly different format. In the physics classroom, it looked like this. A equals the change in velocity over the change in time. But we know change in velocity is simply V2 minus V1 over T2 minus T1. And convention dictates that T1 is almost always 0. So we tend to not write it in. So we have simply V2 minus V1 divided by T. Okay, so even though actually it's the change in time, the initial time is virtually always 0. So we just call it time. So we have the second velocity minus the first velocity. Well, let's take a look at subscripts real quick. This subscript V2 simply means the second velocity. This subscript F simply means the final velocity. They're equivalent. Likewise, V1 means the first velocity, VI means the initial velocity. So they're equivalent. Depending on what book you're looking at or what mood you're in, you can use a VF or a V2. You can use a VI or a V1. They both work. They both mean the same things. Going back to this guy, we're going to go ahead and rearrange it a little bit. First, we're going to get rid of T. We're going to go way over to the other side. Going to get rid of T, put T over here. The T's are going to cancel. We're going to rewrite this. We see AT equals V2 minus V1. We're going to get V1 over on the other side. So we have AT plus V1 equals V2. Well, that's just this guy up here, only with 1's and 2's instead of F's and I's. So that's the first equation. We've actually already used it. The next one is interesting because we've got a DF, which is a final distance, a DI, which is an initial distance, a VIT, initial velocity times time, and a 1/2 AT squared, acceleration times time squared. What's the difference? There's no VF, only a VI. So if you don't know the final velocity, but you're trying to find a distance, this will work. The other difference, this has a distance in it. The other equation had no distance in it. So if you need to find distance, this guy will work. This DI is usually, not always, but usually 0. If it's not explicitly stated in the problem, if the problem doesn't say anything about DI, then you can assume that it's 0, which makes this equation much easier to use then. Again, this DF is simply our final distance. VI we've already encountered, that's our initial velocity. T is simply the time, and A is simply the acceleration. No big deal. Let's look at this one now. This one has a VF squared, a VI squared, an acceleration, and a change in distance. Again, just like before, that distance, DI, is usually 0. So if it's not explicitly mentioned in the problem, you don't need to worry about it. VF is simply the second velocity or the final velocity. VI is simply the initial velocity. Because this DI is usually 0, we usually write this equation slightly differently. So you'll usually see the equation written like this, where it's just a simple D in that final term, which makes it easier. But again, on the equation sheet, you're going to see it like that. What makes this equation special? Well, take a look at it. There's no time. So if you don't know the time, you can use this equation. This is kind of an unusual equation. It only works when acceleration is constant, but those are the only kind of problems we do in high school physics. This has a change in distance again, and again that initial distance is usually 0, so we're really talking DF. And then we have 1/2 times the initial velocity plus the final velocity. So we're finding the average velocity, and then we have time. What makes this equation so special? Well, it has no acceleration in it. This last one is one that we've worked with a lot before. It's our basic velocity equals distance over time, or a special case where velocity average is equal to the total distance divided by the total time. The trick is you can only use those, and only when acceleration equals 0. That is the only time you can use them. That tends to become a problem for people. You've got to remember now, because now we're going to have times when there is acceleration, you have to remember that this can only be done when acceleration equals 0. These guys are special cases. They only work if a equals 0. Do not use them when there is an acceleration. Again, do not use this if there is an acceleration. If there's any acceleration, these guys are bad. No, do not use. Cannot work. Otherwise, they're friendly. So there's our kinematic equations. They're really not too bad. This one here is the first one. It has a second velocity and an initial velocity, or first velocity, but there's no distance in the equation. This one has a distance in the equation. It has the initial velocity, but there's no final velocity. This one has a final velocity and initial velocity, but there is no time in this equation. No time, you can use this guy. No final velocity, you can use this guy. No distance, you can use this guy. And then there's this extra guy right in here that works. I'm not real fond of it, to be honest, because I like the calculus-based ones better, but it works just fine in our classes. So there's no acceleration, you don't know it, you can use this one. And finally, the ones that we've already seen, these guys, v equals d over t, and v average equals d total divided by t total, can only be used, only used when acceleration equals 0. So you have to be really careful with them. Again, warning, warning, warning. Only use those when acceleration equals 0. Thank you very much for your time.